We shall going to start module 3 of chapter 4. In this module, we are interested to discuss Hamilton's equations of motion. In the previous chapter, that is in chapter 3, we have discussed detail about the Lagrangian mechanics. There are another reformulation of classical mechanics which is known as Hamiltonian mechanics. It is defined with the help of Lagrangian. This development provides a better way to describe the equations of motion. It helps us to write down the equations of motion in a simple way and very fascinating way. In this module, our learning objectives are necessity of Hamilton's equations of motion. We shall derive such equations. Conservation of energy will also be discussed. First of all, Hamilton's equations of motion. In our previous module, that is module 2 of chapter 4, we have defined the Hamiltonian. Hamiltonian H is given by summation k equal to 1 to n qk dot into pk minus capital L, which is a function of generalized coordinate qk, generalized velocity qk dot and time t. So, if we consider a virtual change of Hamiltonian H at any time t, then we get delta H equals to summation k equal to 1 to n delta qk dot into pk plus summation k equal to 1 to n qk dot into delta pk minus delta L function of qk, qk dot and t. There are 4 variations: delta H, delta qk dot, delta pk and delta L in equation 4.19. Now, Hamiltonian H is a function of generalized coordinate qk, generalized momenta pk and time t. If we take the variation of this equation, then we have delta H equals to summation k equals to 1 to n del capital H del qk into delta qk plus summation k equal to 1 to n del capital H del pk into delta pk plus del capital H del t into delta t. Again, delta L is given by delta L equal to summation k equal to 1 to n del L del qk delta qk plus summation k equal to 1 to n del L del qk dot into delta qk dot plus del L del t into delta t. Please note that Lagrangian L is a function of qk, qk dot and t, but the Hamiltonian H is a function of generalized coordinate qk, generalized momenta pk and time t. Since delta H given by 4.19 and delta H given by 4.20 must be the same. So, we have summation k equal to 1 to n del capital H del qk delta qk plus summation k equal to 1 to n del capital H del pk into delta pk plus del capital H del t into delta t equals to summation k equal to 1 to n delta qk dot into pk plus summation k equal to 1 to n qk dot into delta pk minus summation k equal to 1 to n del L del qk into delta qk minus summation k equal to 1 to n del L del qk dot into delta qk dot minus del L del t into delta t. We have used the result of delta L. Simplifying, we get summation k equal to 1 to n del H del qk delta qk plus summation k equal to 1 to n del H del pk into delta pk plus del H del t into delta t equal to summation k equal to 1 to n qk dot into delta pk minus summation k equal to 1 to n pk dot into delta qk minus del L del t into delta t. We have used here the result pk equal to del L del qk dot for k equal to 1, 2 up to n. Using this result in Lagrange's equation of motion ddt of del L del qk dot minus del L del qk equal to 0, that is pk dot equal to del L del qk for k equal to 1, 2 up to n. This result is also used in the above equation 4.22. Equation 4.22 is true for all arbitrary variations. Hence, we have del H del qk equal to minus pk dot del H del pk equal to qk dot. These are valid for k equal to 1, 2 up to n and del H del t equal to minus del L del t. Thus, we have qk dot equal to del capital H del pk, pk dot equal to minus del H del qk for k equal to 1, 2 up to n. These equations are called Hamilton's equations of motion of a dynamical system. Please note that for n degrees of freedom, we have two first order equations. These equations are partial differential equations. One can remark that Lagrangian L, which is a function of generalized coordinate q, generalized velocity q dot and time t, it is described always in the configuration space of appropriate dimension, where the configuration space is described only by the total number of generalized coordinates of that system, whereas Hamiltonian which is defined by the function capital H, which is a function of generalized coordinate q, generalized momenta p and time t. It is described in the phase space of requisite dimension set by the equal number of generalized coordinates as well as generalized momenta. Next, Lagrangian mechanics provides a second order differential equation of motion corresponding to each degree of freedom of the system, whereas Hamiltonian mechanics provides us two first order differential equations of motion corresponding to each degree of freedom. Hamilton's equations of motion can only be derived for holonomic dynamical systems, whereas Lagrange's equations of motion can be derived for holonomic as well as non-holonomic dynamical systems. Now, we shall discuss the conservation theorem for energy. If capital H is explicitly independent of time t, then Hamiltonian H can be written as capital H equal to capital H function of qk and pk, k varying from 1 to up to n. Here there is no t as H is independent of time t, so t is absent in the Hamiltonian H. qk is the generalized coordinate, pk's are the generalized momenta corresponding to the generalized coordinate qk of the given system. If we take the time derivative of the Hamiltonian, then we get ddt of capital H equal to summation k equal to 1 to n del H del qk delta qk plus summation k equal to 1 to n del H del pk into delta pk. By Hamilton's equations of motion, we already have qk dot equal to del H del pk and pk dot equal to minus del H del qk. These equations are symmetric except for the change in sign. These equations are valid for k equal to 1, 2 up to n. If we substitute these in equation 4.24, we get dH dt equal to 0, which gives H equal to constant. Moreover, for a scleronomous system, we know that kinetic energy T is a homogeneous quadratic function of generalized velocities. Therefore, if we use Euler's theorem for homogeneous function, then we get 2 into capital T equal to summation k equal to 1 to n qk dot del T del qk dot. Here T is the kinetic energy, qk dot is the generalized velocity. Thus, we have capital H equal to summation k equal to 1 to n qk dot into pk minus L equal to summation k equal to 1 to n qk dot del L del qk dot minus T minus V. Here we have used pk equal to del L del qk dot, and for a holonomic dynamical system, Lagrangian L is equal to difference between the kinetic energy and potential energy. Thus, we get capital H equal to summation k equal to 1 to n qk dot del del qk dot of t minus v minus t plus v. Since in a velocity independent potential field, v is independent of velocity qk dot, so del v del qk dot equal to 0. If we use this, we get capital H equal to summation k equal to 1 to n qk dot del t del qk dot minus t plus v. We have already have summation k equal to 1 to n qk dot del t del qk dot equal to 2t. So, if we use this result in this expression, then we finally get h equal to 2t minus t plus v equal to capital T plus v. Therefore, for a scleronomous dynamical system in a velocity independent potential field, the total energy, that is sum of kinetic energy and potential energy, that is T plus V, remains conserved. By a scleronomous dynamical system, we mean that the system is independent of time t. For a scleronomous conservative dynamical system of n degrees of freedom, the quantity summation over k qk dot into del L del qk dot minus L is a constant of motion, where q1, q2 up to qn are the n generalized coordinates and capital L is the Lagrangian of the system. Let us prove this result. By a scleronomous system, we mean that the dynamical system is independent of time t. For conservative system, the sum of kinetic energy and potential energy remains constant. So, let us calculate ddt of summation over k qk dot into del L del qk dot minus L. Differentiating the first term, that is qk dot into del L del qk dot, we get two terms. Let us first differentiate qk dot. Keeping del L del qk dot fixed, we get summation over k qk double dot into del L del qk dot, which is the first term of the right hand side. Next, keeping qk dot fixed, we are taking the time derivative of del L del qk dot. This has been written in the second term of the right hand side. Next, we get ddt of L. This is the third term of the right hand side. Now, for a scleronomous system, Lagrangian L depends only on generalized coordinate qk and generalized velocity qk dot. So, ddt of L can be written as summation over k del L del qk into qk dot plus summation over k del L del qk dot into qk double dot. Here we have used the chain rule of differentiation. Since L depends on qk and qk dot and qk depends on time t, so we get this result. Qk is the generalized coordinate, qk dot is ddt of qk, which is the generalized velocity. Now, if we substitute the expressions for ddt of L. In the previous equation we get ddt of summation over k qk dot del L del qk dot minus L equal to summation over k qk double dot del L del qk dot plus summation over k qk dot into ddt of del L del qk dot. These two terms come from this one after taking the time derivative, and dl dt gives these two terms. This term, that is last term and first term, cancels each other. So we get this equation, that is we get ddt of summation over k qk dot del L del qk dot minus L equal to summation over k ddt of del L del qk dot minus del L del qk into qk dot equal to 0. Using the Lagrange's equation of motion for the coordinate qk. Thus, we can say that summation over k qk dot into del L del qk dot minus L equal to constant. Integrating this result, we get the final result. For a scleronomous conservative dynamical system, kinetic energy is a quadratic function of generalized velocity. We have proved this result. Using this result, the total energy theorem has been proved in Hamiltonian mechanics. Next, we shall consider a theorem. If all the coordinates of a dynamical system are cyclic, then they can be determined by integration. In particular, if the system is scleronomous, then the coordinates are all linear functions of time t. Now we shall prove this theorem. A coordinate qk is said to be cyclic if it is explicitly absent from the Hamiltonian. We know that Hamiltonian age is defined in terms of Lagrangian as h is equal to summation k equal to 1 to n qk dot into pk minus L. Since qk is absent in the expression of h, so qk's are cyclic coordinates. As all the coordinates are cyclic, so Hamiltonian h can be expressed as h equal to capital H function of pk and t. There are no qk, as qk's are the cyclic coordinates. Here pk's are the generalized momenta of the system having n degrees of freedom. Hamilton's equations of motion give qk dot equal to del H del pk. This can be written as qk dot equal to fk, which is a function of generalized momenta pk and time t, k varying from 1 to up to n. Since qk's are the cyclic coordinates, so pk equal to constant. If we write the constant as beta k for k equal to 1, 2 up to n, then we have generalized momenta pk equal to beta k. Therefore, qk dot equal to fk function of beta k comma t. Here we have used the result pk equal to beta k. This on integration gives qk equal to integration fk function of beta k and t into dt plus integrating constant for k equal to 1, 2 up to n. So, the coordinates can be determined by integration. If someone know the value of the function fk, then qk can be obtained explicitly. For a scleronomous system, qk dot equal to fk function of pk. There is no t since the system is scleronomous. This on integration gives qk equal to integration fk function of beta k to dt plus constant. Here also we have used the result generalized momenta pk equal to constant equal to beta k. Therefore, qk equal to fk function of beta k integration dt plus constant. Since fk function of beta k is itself constant, so we have taken out before the integration. Thus, we have qk equal to t into fk function of beta k plus constant for k equal to 1, 2 up to n. So, the coordinates are linear functions of time t as qk is given by t into any function. In this module, we have obtained Hamilton's equations of motion, which give a better way to describe the equations of motion in a very simple, fascinating way. Lagrange's equations of motion is basically a second order differential equation, whereas Hamilton's equations of motion is a partial differential equation and it gives two equations for each degree of freedom, whereas Lagrange's equation of motion is only one equation for each degree of freedom.